Hi, I'm Erica Carlson, a theoretical physicist here at the Purdue Quantum Science and Engineering Institute. Welcome to Quantum Connections, where we have interesting conversations with scientists and engineers working on all things quantum. Our guest today is Dr. Chandralekha Singh. She is well known in the field of physics education research. Dr. Singh is a distinguished professor at the University of Pittsburgh. She's also director of the discipline based Science Education Research Center. She's a fellow of the American Physical Society. I could go on, but I'd like to start this conversation with Dr. Singh. Dr. Singh, welcome to the podcast.
Thank you so much. I'm delighted to be here.
And thanks for joining us. So, why are people, in your opinion, so excited about all things quantum right now?
I really think this is a very exciting time to be part of this second quantum revolution, the quantum information revolution. And that has been possible because of the fact that we are able to control and manipulate quantum systems in ways that was not possible, like, say, 40 years ago or 30 years ago, even. So, 100 years from the time when quantum mechanics was actually formulated, now we are going to see applications of quantum mechanics in quantum computing, quantum communication, and quantum sensing. So I do feel that this is an exciting time to be part of this quantum information revolution.
Very exciting. Now, what originally got you interested in doing science?
So I actually went to school in an all-girls school in India, and I thought that I was really good in math and science because not only were my teachers telling me I was really good, but also my fellow students. I was always helping all of the other peers in my class. And, I felt really empowered by the fact that everybody was asking me for help on various things. And of course, like I think that in high school, I found math to be really easy. It wasn't like very intellectually demanding at all, whereas physics was much more intellectually engaging. It is your world, know the rules, and you can have like so many different kinds of problems that you really have to think carefully about. So physics interested me the most. So I decided to actually major in physics in college. And ever since then, I've never looked back because it's been really, really fun.
So it sounds like part of the reason you went into physics to begin with is because it's challenging, it's meaty, and it's satisfying when you solve the problems. That was my experience? Was that your experience? That it's part of the fun is that the satisfaction of solving these problems?
Absolutely, absolutely. I absolutely agree with you on that because the fact that it's really challenging, and at the same time, I'm very interested in theoretical physics. So, that's what I did my PhD and postdoc in. And so the point is that, like you get to do these really interesting problems, and physics is so systematic because you can really think about how things work. You have a problem that you're trying to solve that has some real implications for the real world. And then mathematics is the language that helps you actually systematically figure that out. That was really intellectually stimulating. And, I'm still really amazed by the fact that we are able to actually do these kinds of things and understand our universe. So, yes, I definitely embrace that intellectual challenge and excitement.
Very nice, thanks. Now, there's a lot of research going on in your group. Um, One of the things that I find most interesting about your research is that you've been working on ways to help students learn quantum mechanics better. So, could you tell us a little bit about that work?
Yeah, thanks so much. Yes, I mean, I absolutely love quantum physics. So, when I got involved in physics education research, most people were only thinking about how to improve student learning of physics at the introductory level. And by that, I mean at the first year and second year level. So, nobody was looking at what happens to students, beyond that. And so I really thought about the fact that students have difficulties in learning quantum even beyond that. So I got involved in that. So I basically pioneered this thing beyond um, the introductory first 2 years level, and I've never looked back because it is so incredible. to actually figure out what are the kinds of difficulties that students are having in learning quantum, and how research based learning tools can help students learn quantum much better. So basically, we have actually seen that regardless of the kind of universities that students are in, who the instructor is, what the textbook is, what the instructor's teaching style is, students at all the different universities that we have done investigations at have similar difficulties regardless of the background. And so it's in a way universal, like it's possible that only 20% of the students will have certain kind of difficulty in one university versus like 30% versus 40%, but it'll be like very predictable. And then you can really think about how to help students learn these things better by using evidence-based learning tools. And so it's an iterative process, and you need to actually keep doing research to see whether the kinds of learning tools that you're developing are helping students learn these things or not. So we work on, for example, clicker question sequences, and we also develop tutorials, which we call quantum interactive learning tutorials. And these are tools that have been shown to be very successful in helping students learn quantum physics. So yeah, I'm really excited about being able to help students learn this fascinating field that I absolutely love, very much.
Very nice. So, do you find that the difficulties students have are they more at the conceptual level? Because let's face it, quantum is kind of wiggy and has some strange concepts in it. Or do you find that it's more in making the connection between the physical system and the mathematics?
So I would say that one of the things that we find is that the way that people are often teaching quantum, they're not really emphasizing the conceptual aspects of quantum. So making sure that students understand the conceptual aspects of quantum and making that conceptual quantitative connections, those things are extremely important. So all the learning tools that we develop, they focus on making those kinds of connections. So, for example, let me just give you an example of expectation values, right, of different observables in quantum physics. A lot of times, like students will actually be very algorithmic, without guidance and support, because that's what the instructors are emphasizing. And they might just say, oh, expectation value of any observable will be some kind of like integral of psi star operator of that corresponding to that observable psi over integrated over all values, but they may not actually understand that expectation value is the average of a large number of measurements on identically prepared systems. Because those kinds of deep conceptual understanding can really help simplify your thinking and your problem solving. And so basically what we do in the development of learning tools, when we found out that students were having difficulty because of these, lack of conceptual knowledge related to these things, because those things are not being emphasized, we integrated the conceptual and quantitative aspects and had students see how those things connect with each other. And the other thing that I wanted to say is that these kinds of learning tools are particularly helpful for um, equity and inclusion, because oftentimes students from marginalized backgrounds, they have a lot of difficulties, and they don't even feel comfortable asking instructors or asking their peers for help, because they worry about what people will think, because they don't have role models. And there are all sorts of societal stereotypes and biases about who belongs in physics and who can excel in it. But when you actually develop these learning tools that are systematic, that basically start with the kinds of common difficulties that students are having and use them as guide, and build on them, use them as resources and build on them, it really helps all students learn quantum physics much better.
Very nice. Now, you mentioned your tutorials. Are the tutorials available online?
Yeah, so there is a website called Fizzport. So we have a lot of those tutorials available on Fizzport website. In addition to that, now I'm really excited about starting to make some tutorial and also like these clicker question sequences related to quantum information. quantum computing, quantum communication, quantum sensing, more quantum information science and technology related things. And those are things that are really new that you wouldn't find on Fizzboard. But if you're interested, if anybody is interested, we can actually share with them the materials that we have so far.
Well, thank you so much. And what we'll do is we'll put a link in the description to the resources that you're talking about so that we can all access them. Thank you so much for your time, Dr. Singh. It's been a pleasure to have you on the podcast.
Oh, thank you so much, Dr. Carlson. It has been wonderful talking to you.